Hello everyone, my name is Rajesh Jayaram, and in this talk I'm going to tell you about testing positive semi-definiteness via random submatrices. And this is a joint work with Ainesh Bakshi from CMU and Nadia Shepurko for MIT. So I want to begin with just recalling the definition of what it means to be a PSD matrix. So given a real valued square matrix A, we say that A is positive semi-definite if it defines a non-negative quadratic form. Namely, if for every x in Rn, the quadratic form xax is always non-negative. Now, recall the further fact that if A is a symmetric matrix, in addition to being real, its eigenvalues are also real valued. So we can order its eigenvalues, lambda 1, lambda 2, up to lambda n. And if this is the case, then it also happens that the characterization of A being a PSD matrix is also that all its eigenvalues are non-negative. So if A is symmetric, then A is PSD if and only if all its eigenvalues are non-negative. And then one additional fact, which will be very useful for the purposes of this talk, is that if A is a PSD matrix, then all principal submatrices of A are also PSD. So here, a principal submatrix is just the square submatrix obtained by selecting subset T of the n rows and columns and looking at the square submatrix with the rows and columns both that are in T. So if A is PSD, all such principal submatrices are also PSD. So why would we want to test whether a given matrix is PSD? Well, it turns out that there's a very large number of reasons why one would want to test PSD-ness of a matrix. And in fact, in many computer science applications, testing whether a given matrix is PSD is a crucial subroutine or bottleneck in the algorithms. So for instance, if you have a function, testing whether your function is locally convex reduces to testing whether the Hessian is a positive semi-definite matrix. Similarly, testing whether a finite metric can be embedded in Euclidean space by Schrodinger's criteria, this reduces to testing whether a specific matrix is positive semi-definite. Similarly, you may recall that in a SDP, in a semi-definite program, one of the crucial constraints is that the current variable matrix is a PSD matrix. So when there aren't too many linear constraints in a SDP, testing whether a given matrix is PSD is the bottleneck for testing feasibility. And there's a number of other applications, for example, specialized solvers for linear algebraic problems, and many more that I won't talk about here. But for the purpose of this local algorithms talk, I want to start with a local algorithm that we can keep in mind for the entirety of the talk. And this is as follows. We already recalled that if A is a PSD matrix, then all of its principal submatrices are PSD. So a simple algorithm for testing PSD-ness is to sample a collection of random submatrices, principal submatrices as shown here, and check if any of them are not PSD. If any of them fail to be PSD, we immediately know that A is not PSD, and we can return not PSD. So in other words, this algorithm, the simple local algorithm, has one-sided error, because if A is PSD, we'll never output not PSD. On the other hand, if A is not PSD, it's not clear how large of a submatrix we need to sample for this algorithm to work. So one of the main focuses of this talk is to understand when can this simple local algorithm work? When can we test the semi-definiteness of the matrix by these submatrices? So as I just said, this general question that we address in our work is it possible to test the definiteness of a matrix A by checking the definiteness of random submatrices of A? And so this local algorithm is more or less what we'll consider in the entire talk. Okay, but in general, we know that this is not possible because if we want to solve the problem in general, we'll need to read all the entries of A and not just test random submatrices. But in order to make this possible, we consider the problem from the framework of property testing. So in the property testing model, we assume that our input either satisfies the property, namely here A is a PSD matrix, or that it's far from satisfying the property in some appropriate notion of distance. So A would be either PSD or is epsilon far from PSD in some notion of distance. And so the goal is to test this property using as few queries to the entries of A as possible. So we'll be considering query complexity in this talk. And so I'll mention that this restriction there's a restriction here that the entries of the matrix be bounded. So this is known as the bounded entry model. And it's easy to see that if you want to test any spectral properties of your matrix, you need boundedness. Otherwise, one could just hide a very large positive or negative entry somewhere in the matrix, which would drastically change the spectrum of the matrix, but as a result, you'd have to read the entire matrix in order to notice this entry. So this model has been considered in the past by Balcom, Lee, Woodruff, and Zhang, who gave a number of algorithms for spectral testing properties in this model. And so now I'll discuss what I actually mean by what it means to be far from PSD. And so there's two notions, and one is going to be more specific than the other. So the first one we call the L2 squared gap. And so this just means the squared L2 distance from A to the nearest PSD matrix B. So here this notation, B greater than or equal to 0, means that B is a PSD matrix. And the reason we're considering square distance is mostly just for simplicity. This would all work out even if we didn't want square distances. But we had this nice identity for L2 that the distance from A to being a PSD matrix is actually equal to the sum of squares of negative eigenvalues of A. So in this case, this identity here holds, and we say that A is epsilon far in L22 from the PSD cone if the sum of squares of negative eigenvalues is at least epsilon n squared. And notice that this is also corresponds to the distance, the L2 squared distance, from the vector of eigenvalues of A from being a positive vector, because that's the sum of squares of negative eigenvalues. Now, this is the sum of squares of negative eigenvalues, but a specialized gap, which we call the L infinity gap, is saying that there's at least one negative eigenvalue whose size is at least epsilon n squared. And let me just note that for both of these definitions, the reason we have the scaling of n squared is because our matrix has bounded entries. So the furthest you could possibly be from a PSD matrix is n squared. For example, the 0 matrix, so which is a PSD matrix. So the scaling here says that in the L infinity gap, there's at least one eigenvalue that has value negative epsilon, and that has squared value at least epsilon n squared. And again, this is the same as the L infinity distance of the vector of eigenvalues from being a positive vector. So here I'm just going to show the two definitions side by side. This is the sum of squares of negative eigenvalues being at least epsilon n squared, and this notion is just the maximum negative eigenvalue. And notice that just because of this definition, if you have a matrix with epsilon L infinity gap, this immediately implies that that matrix has epsilon L2 gap. But on the other hand, it's easy to see that the converse is not true. And a good example of this is the class of random matrices. So if I have a bounded random matrix, for example, a random plus or minus 1 matrix A, then it's easy to see that A is constant far from PSD in L2 distance, but only 1 over n far in L infinity squared distance. So there's a large gap for examples of this form. So now I'm going to go through our main results for these two testing problems. And our first result is for this special case of the L infinity gap. And we show tight bounds for this problem. We show that there's a non-adaptive sampling algorithm which solves the PSD testing problem making only 1 over epsilon queries. So here the tilde O only will hide log 1 over epsilon factors. So there won't be any log n terms in this talk, only log 1 over epsilon factors. And then similarly, we show a lower bound for that even adaptive algorithms require 1 over epsilon queries. So we have tight bounds for the L infinity gap problem up to log 1 over epsilon factors. Next, we show an algorithm, an upper bound, making tilde O 1 over epsilon to the 4th queries to solve the more general L2 gap problem, L2 squared gap problem. And we complement this algorithmic upper bound with a lower bound that says any non-adaptive algorithm that solves this problem must make at least 1 over epsilon squared queries. So we characterize the complexity in the case of L infinity gap problem, but there's a small gap for the case of the L2 gap problem. So I'm just going to show these results in this slide right here. And we can see that the upper bound for the L infinity gap problem is 1 over epsilon. But we have a lower bound. This is a tight upper bound, by the way. But we have a lower bound over here, which is strictly larger. It's 1 over epsilon squared. So what this shows is the L2 gap problem is a strictly harder problem than the L infinity gap problem, which we can keep in mind for the rest of the talk. And now I just want to talk briefly about some related work before I jump into our algorithms. And I want to note the bounded entry model that's used in this work has been considered several times in the past, most notably by Balcom, Lee, Woodruff, and Zhang, SOTA 19, to test many spectral properties in matrices. But this is sort of a follow-up work to a line long of work on testing a number of matrix properties, such as matrix rank. And if you want to test spectral properties like spectral norm and stable rank, then you need to work in the bounded entry model. And there was a prior bounded row model as well, which considered it's a weaker model where the rows need to be bounded. But more generally, the bounded entry model is sort of a natural subclass and restriction of the linear sketching model to the class of sampling algorithms. And the reason is that linear sketching sort of gets to look at all the entries of the matrix in some way, but sampling does not. So in this case, we need bounded entries. And because of this, there's many lower bounds to sketching which carry over to the bounded entry model. For example, for Schatten norms and spectral norms. So there's a very close relationship between these two models. And so some algorithms and some inform the other and vice versa. So now I want to jump into just give a flavor of the algorithms and lower bounds in this work. And I'll start with the first algorithm, which is a precursor to the other ones. And this is the L-infinity gap algorithm. And the underlying idea behind this algorithm is that because we know that there's one large negative eigenvalue, namely this eigenvalue x, we know there's some x where the quadratic form is very negative. So in this case, if you have epsilon gap, the quadratic form is less than negative root epsilon n for some vector x. So the idea is going to be to push forward on this single vector down to a submatrix and show that this direction still has negative quadratic form. Specifically, if we sample a large enough submatrix, at by t, we want to hope that when we project x onto those coordinates in t, the quadratic form with a is still negative. In which case, we can immediately conclude that this submatrix is not PSD, and we can test this fact after sampling it without even knowing the vector x originally. So x is only going to appear in the analysis. So the picture is something like this. We know that we have some vector x, which has very negative quadratic form. So we're going to randomly sample a subset of coordinates and project x onto that subset. And then we're going to consider the quadratic form of x on that subset of coordinates with the principal submatrix. And we're going to ask whether it's negative. If we can show that this quadratic form is negative, then we conclude that this submatrix is not PSD. So what we're able to show is that if you take a k by k submatrix, where k is at least 1 over epsilon, then this will suffice to prove the statement in the prior slide, that this quadratic form will be negative. And the proof isn't very complicated. We just consider this random variable, this random quadratic form, which is x projected onto a subset of coordinates, the quadratic form with a. We just compute the expectation and variance of this random variable, show that it's negative with good probability, and apply Chebyshev's. And then this gives this result. On the other hand, it's a k by k matrix. So the complexity here is actually 1 over k, epsilon squared, because k is 1 over epsilon. But recall that our goal is slightly better. It's 1 over epsilon, total complexity. So the first hope is that maybe we can improve the analysis here and do better with one submatrix. It turns out that this is not possible, and it's not difficult to see why. The reason is, if you have a matrix like this, you can sort of hide all the negative mass of the matrix in a very small subset of columns. So here, we hide all the negative mass of the matrix in a small subset S, which constitutes only an epsilon fraction of the columns in A. So if you have a k by k matrix, k needs to be at least 1 over epsilon in order to at least intersect this. And in fact, this gives a general 1 over epsilon lower bound for any even adaptive algorithm. But the solution and the high-level idea that what we can win in this case is that if you're going to hide a large fraction of negative mass in a small fraction of the rows and columns, then that negative mass needs to be very concentrated. And so that one could hope that we'd only need to see a couple entries in it to deduce non-PSD-ness. And that's precisely what we're going to do. The algorithm at a high level is to sample submatrices at log 1 over epsilon scales. And here a scale is a possible side length. So for all possible side lengths, alpha over epsilon, where alpha ranges between epsilon and root epsilon, we sample epsilon over alpha squared submatrices of that size. So at each possible level, you can see that this works out to make a total cost of 1 over epsilon samples per scale of subsampling. And then we show that at least one scale of subsampling, one of the matrices that we sample will be not PSD. And the total complexity will then be tilde O of 1 over epsilon. But the main challenge here, and the core challenge of this work is that, or this algorithm, is that when you move to smaller submatrices, and now may be the case that X is no longer the right direction in which to have non-PSD-ness. So specifically, it may be the case that the quadratic form with X is positive in the direction that we were originally hoping to use, despite the fact that the matrix itself, the principal submatrix, is not PSD. And this can actually occur. And in this case, we need to switch our candidate direction. And I won't go through this in too much detail, but here's an example of from the prior slide, where we have a mass concentrated in a small number of rows. But if we use the original eigenvector x, the quadratic form will be very positive. And this happens because some of the coordinates of x can be much larger than the other coordinates on that small subset. But just skipping past this, the main solution to this is a step which we called eigenvector switching. And roughly what we're doing here is we're swapping from one vector and designing a mapping from our original eigenvector x to another eigenvector y, which will correspond to some rescaling of the entries by the L2 norm of the negative mass of those rows. And what we're able to show is that conditioned on our sample intersecting the small subset of heavy rows, we can actually show that this quadratic form with this new switched direction is negative for some level of sampling in excitation. Furthermore, we can use the conditional variance and some further computations there to show concentration of this random variable at the right level of subsampling. And this will give us our 1/epsilon algorithm. Okay, so in the remaining time, I'm going to talk about the L2 gap problem briefly, and then the lower bound. So at a very high level, the L2 gap problem, the algorithm for this problem is substantially more involved. And the reason behind this is that when you have the L2 gap, you're not promised that any one vector will stand out and will be very negative eigenvector. So the negative eigenmass of the matrix can be spread out over many very light negative eigenvalues. And in this case, this program of trying to push forward the quadratic form projecting onto a subset of coordinates will never have a concentration for any fixed direction x. So we're not going to be able to preserve the negative quadratic form in any one direction. So our solution at a high level is that we are going to need to indirectly infer the existence of negative eigenvalues in the matrix A without showing that any one given direction preserves its negative spectral mass. And the techniques involved in doing so draw heavily from random matrix theory. And I don't have too much time to talk about them here, but I'll note that there's several key barriers in improving beyond 1/epsilon to the fourth. And now I'm going to talk about the lower bound, which complements this upper bound for L2 gap problem. And the high-level idea behind this lower bound is it's, in fact, a very general construction about constructing locally indistinguishable matrices that have some gap in their spectrum. And because all you need is some gap in the spectrum, this will immediately apply lower bounds for a number of other spectral testing problems. For example, testing the Schatten-1 norm, the Chi-Fan norm, and residual error testing. So we obtained some new lower bounds and an improved lower bound for Schatten-1 based on this one construction. And the construction looks something like this. What we're going to do is we're going to construct two explicit so-called locally indistinguishable matrices, G1 and G2. And G1 and G2 are going to have some gap in their spectral properties. So for PSD testing, we would like them to have a gap in their minimum eigenvalue so that one can be made PSD and the other far from PSD. This local indistinguishable property essentially means the following. It means that if I have any small set, and small is something technical here that I won't get into, but if any algorithm makes a small set of queries to one of the matrices, and it sees, for example, these entries here, 0, 1 in this column and 0, 1 in this row, then there exists some unique permutation of the matrix G1 that sends it to the columns of G2, such that under that permutation, you would have seen the same exact entries. This permutation is just a relabeling of the names of the indices had you been looking at the instance G2. So in other words, any algorithm which only samples a small subset of queries can have no advantage whatsoever in distinguishing G1 from G2. The variational distance between the two distributions will be identical. It'll be 0. And I don't have too much time to say on how these instances of local indistinguishable matrices are constructed, but I'll say it starts with a construction based off of a union of cycle graphs, either a single union, either one cycle graph, and this is the adjacency matrix, or a disjoint union of cycle graphs. And then we proceed to apply some amplification steps to boost the spectral gap between these two matrices. But once we have these indistinguishable matrices in hand, what we can do is construct a sparse instance where we plant many copies of this indistinguishable matrix. In one case, we plant G1, and the other case, we plant G2. Then any algorithm that's non-adaptive, when it samples a bunch of entries, only a small, like I say, an epsilon fraction of the entries which this algorithm samples will actually end up in a planted matrix, or we call them graphs in the paper. And if this is the case, then each of these graphs will be robust to this, each of these individual matrices, because we said that they're locally indistinguishable. And so any algorithm which sees such a subset of queries will have no gain in distinguishing one example from the other. And so I'll direct you to the paper for further details on this construction. And finally, for some quick open problems, I want to mention that the main open problem here will be to close the L2 gap. And I think this is a very interesting problem because there's several key barriers coming mainly from limitations of techniques in random matrix theory to improving the upper bound B1 to 1 over epsilon to the 4th. And I think it would be very interesting to see if new techniques beyond those that are currently known are capable in showing concentration of eigenvalues that gives better upper bounds for this PSD testing problem with L2 gap. And finally, I want to mention that with this work, this is just, we've added another lower bound to already a collection of known lower bounds for the Schatten-1 testing problem in the bounded entry model. And there's also a number of lower bounds in the sketching model. But so far, there's no non-trivial upper bounds that are known for this problem. And I think it would be very interesting to design improved non-trivial upper bounds for testing the Schatten-1 norm in the bounded entry model. So that's all for this talk. Thank you so much.